Efros. He is a professor at UC Berkeley, and the Berkeley Artificial Intelligence Research Lab. His main research question is how to deploy large amount of abundant labeled data, unlabeled data, to understand the visual world among us. So let's see how the talk will go, and he will discuss the challenges and the benefits of learning out of the standardized benchmarks scenario. Okay, please, let's welcome.
All right. Thank you very much. Can you hear me?
Yes, very well.
Wonderful. Yeah. Okay, so thank you. I just want to preface my talk with the disclaimer that I'm not really an ML researcher. My work is in computer vision. So this talk would be a little bit of like a dilettante's outsider perspective. So I can, I'm very likely to say things that are wrong. So please do, do correct me. And so the hope is that this is kind of like a view from the outside. Okay. And second is when my wonderful colleague, Saina, my Berkeley colleague, invited me to this talk, to this workshop, she gave me strict instructions. She said, don't just rehash your old papers, do something new, be controversial. So Saina, I hope that I don't disappoint, but here you go. I thought we can think about what would it be like to live in the next post-dataset world? And let's imagine what it would be like, okay? Of course, to predict the future, we want to first understand the past. And so the pre-dataset world, I actually still remember. I started my PhD in computer vision in 1998. And let me tell you, it was a very different world back then. There were no tables, no data sets, no numbers, and basically the papers had equations and a few images. In fact, the CUPR joke in the 90s was that, how do you know if a paper is good? Well, if the paper only has a single image, it's probably a hack. They just basically, it only works in one image. If it has two images, oh, it's an algorithm. But if it has three images, it's a framework, okay? And I was thinking, how true is this? So this week I actually went back and picked one of the most famous papers in computer vision, Canny edge detector. Everybody knows that, 35,000 citations. And then I just counted the number of images in there, and guess what? 1, 2, 3. So there you go. It's a framework. No wonder it's so famous. Okay, it actually had worked on more than one image. But then around the turn of the century, things started to change. And for me personally, I was observing this change in my office. My office mates were doing stuff that was, David Martin, my office mate, was like, he came from systems, and he was like, well, if I want to do an edge detector that, how do I know I'm going to be better than Kenny, right? There is no way to tell. Like, how do I just look at a few images? And so what they did is they said, okay, let's just measure things. So they got a bunch of people to label edges, and I was, I think, one of the people who did it. And then finally, you could actually get some numbers, and you can get some PR curves, and you can actually tell that here is the blue curve, that's Canny, and then you can see a bunch of algorithms that below Canny, and you see some algorithms above, and you can also see there's this wonderful green dot, and the green dot is human performance. So you can actually even have kind of an estimate of the best case scenario, right? You look at the cross human performance, and that really changed the atmosphere. It really felt like we were becoming a science. And so kind of the dataset era was like around 2000 to the present, and a lot of the important contributions were actually data-driven breakthroughs. So I'm sure everybody here would know SIF descriptor, but probably most people don't know that the SIF descriptor wasn't immediately famous. The SIF paper was ICCB 99. I was there. It was a little humble poster in the corner. I was the only person there, first-year grad student. Nobody really cared. What happened, though, is that 4 years later, Christian Mikolajczyk and Cordelia Schmidt decided to run a study of different descriptors, and they thought, oh, we'll include this silly David Lowe SIFT thing. Why not? Let's try it. And it completely blew everything out of the water. And that's how SIFT became SIFT. It became SIFT because of the data set that showed that it was good. The same thing with deformable part models that really became famous because they kept beating everybody on Pascal detection. And of course, the most famous is convolutional neural networks that were around since 1980s. But really, it was they're beating everyone on ImageNet and then Pascal that really kind of solidified their prominence. So that was really a fundamental use of data sets. But interesting, at that point, data sets were really more thought for evaluation rather than training. The idea was that you can train on anything you want. This is really just kind of to evaluate how well you do. But then by and by, people started to just think of data set training on that same data set. And that is where we started to get into problems, okay? So for example, you want to detect cars, you pick a data set, say MSRC, and you train a car detector on that, and you think you're detecting cars. But in actuality, you're detecting MSRC cars. And then when you run this detector on other data sets, it basically doesn't work, right? Because you're not actually detecting what you think you're detecting. You're not looking at cars. You're looking at the very specific subcategory of cars that are captured by MSRC. Okay? And of course, the reason for this, as we now know, or large part of the reason, is the dataset bias. So here is an example of cars from different popular data sets of the day that Antonio Torralba and I looked at. And you can see that actually they're all cars. They're all sampled from the same domain. It's not like the domain is different. No, the domain is cars. It's just that every data set captured a very biased subsample of that domain. And so by training on one, you cannot guarantee yourself doing any good on that, okay? But things are actually, I would argue, a little bit more worse and more complicated than that. So here is an example from action recognition that David Fui showed me. So action recognition, you get a video. Let's say you're opening the fridge door, you're pulling the door, you're opening the fridge, you're closing the fridge. And then the task here is, output the class label. Are you picking up cup? No. Are you slicing bread? No. Are you opening fridge? Yes. Okay. And all the methods do fantastic on this kind of task. This action recognition, 99.999% performance. But is it actually solving the task? Well, not really, because it's not actually looking. It's not detecting the hand. It's not finding the door of the fridge. What actually it's doing, it's really not even looking at most of the frames. It's really only looking at one frame, which is the texture inside of the fridge. Okay, and that alone is perfectly enough to do well on this particular task. So it's basically cheating. Okay. And you could say that, well, this is a data set bias issue. You need to go to IKEA or Home Depot and take pictures of open fridges and put it as your negative set. But I would argue that in that sense, it will never go away. This problem will always be there because your data set is finite. So there will always be some way to cheat. If you want to cheat, there will always be a way to cheat. And so in a sense, that kind of like stationary data set learning becomes kind of akin to memorization. So if you remember college, let's say there was a class you didn't go to for a whole semester and tomorrow is a final exam. So what do? You get a whole bunch of previous exams and then you do learning, right? You basically say question, answer, XY pairs, boom, 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 boom. And you just memorize them, right? And, we all know that cramming works. So you go and you take the test and you do actually pretty well, okay? Now, have you learned the material? No, but you passed the test. So the bigger worry here is that we're raising a generation of algorithms that can only cram for the test set, but don't actually learn the material, okay? And I think this is kind of a fundamental problem, and I hope that I could convince you that continual learning might be a way to deal with it, okay? So what can we do? Well, one thing we can do is kind of the Berkeley New Age Montessori feel-good approach, which is let's just get rid of the tests. no exams, no finals, no grades, unsupervised learning, some self-supervised learning, intrinsic motivation, curiosity. Basically, the argument is if you don't have an objective, there is no way you can cheat because you don't know what to cheat to for, right? And so you get away from cheating by not telling what we want. And this, I think, is a reasonable way to do it. But the problem is that then you have no control about what is being learned. And you might learn something about the world that's maybe useful to something, but like completely useless to you. Okay, so that's kind of the problem, that you don't know what you're going to be learning this way, right? Although this is definitely something that, like, in my group we've been working many years on this direction. But here I want to kind of propose a different direction, which is kind of the opposite. If the first one is kind of the Berkeley Montessori school, this is my Soviet school, when I was a kid, which is basically brutal daily homework, 7 days a week, and just no let up and no mercy. Okay, and to me that is basically what I think of as continual learning. And I know that maybe you folks might disagree, and this is the kind of stuff where we are kind of interested in doing things like test time training, and also thinking about a kind of a world without a fixed data set. Okay, so let me talk about this for the remainder of this talk. Okay, so what do I mean, no fixed data set? Why no fixed data set? Well, so the motivation, one of the motivation is from the real world. In biology, biological agents, they never see the same data twice, right? That's just not possible. Every time they see something, something is different, right? So they have a very different way of absorbing the data, right? Every piece of data is first it's a trained test set, and then it becomes training set, and then it gets incorporated, and then you continue on like this throughout your lifetime. Okay, and one could argue, but this of course needs to be evaluated more, but that it could be that repeating the same sample over and over again might encourage this kind of memorization and cheating, and discourage the generalization that we want, right? So it could be that we're actually screwing ourselves up by having these multiple epochs. And this also might explain why data augmentation works so well, because data augmentation actually gets you out in a limited way. It gets you out of this repeating the same thing over and over regime, because every time you augment in every epoch, it's something a little bit different, right? So it could be part of the reason that the data augmentation works so well is because of this. And frankly, if you're working in self-supervised learning, I don't think there's any excuse for multiple epochs. I mean, there's so much data in the sea. Just always use new data. There's no reason to ever go back if you don't need to. Now you could say, wait, what about consistent evaluation? How do we compare different algorithms? And I think this is okay. This is a fair point, especially if you want to have like a labeled test set. But it's not like other fields haven't grappled with this. Plenty of other fields have kind of evolving test sets, and they're doing fine. Healthcare, polling, stock market, they can deal with continual testing, and I guess it's more work. You need, your error bars are going to be bigger, but we know how to do it. There is plenty of good statistics, approaches that tell us how to deal with this in the right way. And it might be that this is actually kind of a much more robust way to evaluate performance. Like you might be less prone to overfitting to a particular data set. So I don't feel like this is really such a kind of deal breaker. Now, why continual learning? And here again, I think that my way of thinking about continual learning might be different from kind of the majority of folks, but hear me out. So to me, continual learning is kind of like a generalization of validation set. Okay, so let's say you have your training set. Let's say it's fixed. Okay, and now we know that it's often good, or almost always good, to split that up into a train set and a val set. So you reduce your training data. So you think, wow, this is crazy, right? You're reducing your training set. And then you save a little bit of that data to validate your hyperparameters, okay? And we know that for most cases, this works better than if you just used all the original data at once as training, okay? Well, now let's see if we can generalize this a little bit. Instead of a single validation set, what if we have infinite validation sets? In fact, what if we could continually validate what we are doing? So we have your training set is basically all the data you have already seen. And your validation set is that new sample that you're just seeing right now. So now you use it as a validation sample. And then in the next step, you incorporate it into your training set, and then you go and you continue and get to the next one. And I argue that this kind of way of thinking about continual learning as kind of continual validation, I think it's not a bad way to think about it. And we have some very preliminary evidence that this actually does work better than kind of the standard setup. So this is maybe different from kind of the standard thing, but I think also not, because a lot of work for something like something like RL basically does do very much this. Okay, now one argument that people could say is, what about catastrophic forgetting? Okay, and here again, I'm not an expert, but I'm wondering whether catastrophic forgetting people got a little bit too focused on that. Is it really that catastrophic? And so here is my argument. So there are two cases I can see. Case one, if you don't want to forget all data, right? You don't want to forget something that you have seen before. Doesn't this mean that your distribution is actually probably stationary, and that you are just getting a very kind of a biased sampling? You're very not IID in the way you're looking at the data, right? But if your distribution is stationary, then we know how to deal with it. Like, one way is to just get a big buffer and just turn things into IID. Another way is maybe to look at some other ways to optimize your method that doesn't require you to be IID. So I think this is kind of an interesting direction, but this is something that's not so bad, I would say. That, like, we know ways to deal with it. Now, case two is if your data is actually shifting, right? That you actually do have a domain shift going on as part of your learning. But then if your data is shifting, I'm not sure you need to worry about remembering all data, because that data will be stale. That data might not actually be something to remember. It might be good to forget, okay? And so again, it's not clear that you need to really worry about it that much, okay? Now, I think the one important thing though here is that these domain shifts cannot be abrupt. And so here's my kind of, and this is kind of an argument against all these kind of discrete tasks that are kind of popular in the community right now. I think that's not the right way to go. And here is my kind of hand-waving motivation. Evolution rewards adaptation. That's true. So you take a field mouse and you put it in your house, and within a day, the field mouse will be just like at home, and he will eat all of your food, and everything will be great. So wow, this is such an amazing adapter. But there's a little bit of kind of this survival or observational bias here, because we think of all the successes of adaptation, but we forget about all the failures of adaptation. Jeff actually reminded me of the paper that we had a couple of years ago, where we basically made completely impossible to play games, and showed that this is one case where you don't generalize. You're just really bad. No matter how good you're at playing games, you'll be horrible at our games. So go to our webpage and try it yourself. So that's why I feel like it's very important to have another constraint. And I think the right constraint here is smoothness. That the shifts need to be smooth. And that seems like the right thing for our algorithms, but it's also the right thing for evolutionary. So kind of an example is, as I mentioned in the panel, if your oxygen levels on Earth drop by 50% tomorrow, we're all dead. Maybe not the cockroaches, but everybody else is dead. But if you have the same drop, but over 1,000 years, it's all fine. Evolution will take care of it. It's slow enough, it's smooth enough that we will all adapt. Okay, and so that's kind of a fan wavy motivation why this is, I think, smoothness is important. Okay, so now finally, enough with this philosophical mumbo jumbo. I can actually talk about something that we're actually doing. And this is, of course, going to be much less ambitious, but maybe hopefully in the same direction. So our attempt is to operationalize this type of continual learning on infinite, smoothly changing data stream. Okay, and the core idea that we've been using for several years is to use self-supervision as a way to continually adapt to the new data. So instead of being invariant to all the changes, we're just going to adapt to those changes with self-supervision. Okay. Now we have already showed this works in the context of RL with our curiosity work of Deepak Pathak a few years back, and now we just want to see, okay, what happens if we push it more towards computer vision area and away from RL. Okay. And one inspiration that is just a fantastic paper, and I'm just want to advertise it because it's such a beautiful paper. And many people don't know about it. This is from Michal Irani's group. Is the idea of one sample learning, and in this particular case, their task is super resolution. So you get a small image, and then you blow it up to be large, right? So the classic way to do super resolution is with deep learning, you get a whole bunch of training data, small images, big images, you train a big model, and then at test time you have a new image, you apply this model, you super resolve your image, right? Well, what they do is something completely different. They don't have a training set at all. They do everything at test time. So what they do is at test time, you get an image, okay? Now you sample this image, you reduce it by half, and then you train from scratch a network that upsamples that reduced image back to the original test image. So that's your training phase that you do at test time. Okay. Now, once you're done that, you just take that network that you just learned and just apply it to that same test image to upsample it again, basically. And this is just so simple and so brilliantly beautiful. And the best part is it actually works really well. So here is an example. Here is a small image. Here is super resolution using standard machine learning. And this is super resolution with their what they call internal machine learning. So I'm going to flip between them, and you can see that it's actually working really, really well. Okay. So that was really a big inspiration for us. Okay. And then we thought, okay, but this is really getting rid of all extra data, just really completely, algorithm that has a total amnesia, right? We do want to somehow also remember the stuff we have seen before, but also use this idea of training at test time. Okay, and so this is a paper that we have at this ICML. Just presented, and I'm just going to give a quick summary of this. And the task here is to generalization on under distribution shifts, but I think it works in many other domains as well. And basically, the story is your standard, at test time, your standard test error is, you have a test distribution queue, and you're basically trying to see how well you're doing. And the note here is that when you're looking at the test sample X, that test sample, just the data, not the label, but just the data itself, gives us a hint about our test distribution Q, right? It knows something about Q, and it would be great if we can somehow use that information, right? And so what we're going to be doing is now we're going to basically make the parameters of our model depend on our test sample X, okay? So now the model is not fixed. It adapts over time, okay? And it becomes like a one sample problem, just like Michal Arani's. And the only problem, of course, is where do you get the label? And this is where we use self-supervision. Okay. And so basically, the algorithm is kind of pretty simple. It's kind of pretty standard nowadays. You have two heads. You have the standard head, which is your main task. Let's say object recognition, and then at the same time you also have a self-supervised task. In this case, we just use the rotation prediction. We take an input image, randomly rotate it for one of four ways, and then try to make it predict which rotation it was. Okay. And these are the two things that we are training. Now, at test time, of course, we don't have the labels anymore, but we still can do the self-supervised task. And that's what we're going to be doing at test time. So we're doing the self-supervised task at test time, and we are, and because they are sharing some of the parameters with the main task, the hope is that it will also be getting better. You're going to be adapting that task as well. Okay. And in fact, that's what we see here. So here is an example, an elephant. And if just out of the box, off the shelf model, it actually thinks it thinks it's a dog rather than an elephant in the beginning. But after just a few gradient steps of this test time training method that we propose, it basically figured out that no, this is actually an elephant, and it got there. Okay. And so we have two modes for this process. One mode is kind of what we call standard version, where every test sample is kind of independent, and we basically forget everything after we use a test sample, and then we start from scratch again. Okay. But I think a more interesting mode for this audience is what we call online version, which is that we just keep adapting our model one sample at a time as the samples are arriving at our stream. And so now here we do have an assumption that the distribution of those samples is either the same, which is not that exciting, or it could be changing but smoothly. Okay. And then it still works. Okay. And so then we tried it on various tasks in the paper. Here I'll showing you just the task of going from still images to videos, which is a hard task, and you can see that it's actually it beats kind of standard joint training. It beats like just one task. It beats joint training, and the online version is actually a little bit better than the standard version, to kind of showing you that you actually do kind of you are learning something as you're going along in this fashion. And then just recently, we also produced a version of this for in terms of policies for deployment. And here I'll just show you the video. So you train on one thing, and then you're testing it on a new scenario, and the new environment is changing. You can see the background is changing, and that totally screws up these baseline methods. But our method, because it's able to continuously train at test time, it's able to cope with them and deal with those continuous changes. Okay. And finally, another paper that we just produced is a way to kind of use this kind of self-supervision to learn correspondence from video. So again, very much kind of a continual learning friendly problem. You get a feed of video, and then you basically want to learn about the world from that video. And the way the idea is actually very simple. So imagine if you had correspondences, then we could use these correspondences to kind of or faraway things to learn about the intermediate things. So we can learn intermediate correspondences from faraway correspondence. Now, of course, we don't have any correspondences. We don't have any supervision. But what we can do is we can turn this video into a palindrome by going backwards, flipping the video and going backwards to where we started. And now the problem becomes that of kind of ending up where you started within this palindrome video. And so this is very much a self-supervised learning problem. Okay, and we basically need to find the latent correspondences. And the way we solve it is we're basically just going to do a random walk on this. We turn the video into a graph. this palindrome video intake graph. And now we're just going to do a random walk on that graph, but we're going to guide this random walk so that it ends up at the place where we started, and we're going to guide it with a contrastive loss. Okay, so a very nice. I'm very happy with the kind of formulation. It's very simple and very nice, and it's beautifully well chosen for the kind of task that we want, the continuous learning task. And so here I'm not going to show you anything except show you that we actually, so this is the baseline, and you can see that this is propagating masks in a video, and you can see that we are able to better deal with occlusion than the competitor. And the nice thing is that doing this in kind of this test time training wins us, some over just doing it in a kind of standard, training testing split. Okay, so to conclude, data sets were very useful to establish computer vision as like a real science, but I wonder if they might be starting to hurt us now. And so I want to think about starting to kind of moving away from this kind of fixed training test set, fixed data sets, and more about continuous data streams. And this idea of test time training, I think, is one way to kind of tackle this using self-supervision. Okay, so thank you very much, and I'm happy to answer questions.
Thank you. Thank you very much. This was a wonderful talk. We have a few questions on Slido, but I'd like just to remind those in the Zoom session, if you'd like to ask any questions, please raise your hand and we'll unmute you so you can ask your questions directly. So the first question is, in the context of little domain shift and continual validation, how is your view of CL different from online learning scenario?
So again, as I'm an outsider in this, I don't actually see. I think this is indeed an online learning scenario, but I think it's in a sense it's both, because if you're an online learner, it's very hard to have online things that are online being IID, right? It's like it's very, very rare that somehow there is some amazing IID gun that is shooting your data at you at exactly IID, right? So your data is going to be not IID. It is not going to be in equally distributed. So you are going to basically be kind of meandering between little subdomains all the time, right? And so I think these two things are actually not that different, because you need to deal with a change in domain and smooth changes in domain every time you're using online learning anyway. So I think, yeah, to me, those two are not that different.
The next question is maybe slightly a little bit more open-ended. So per your final comment in the panel, what do you consider an accomplishment in the field of continual learning that would make computer vision people curious to apply continual learning to their problems?
Yeah, very good question. I think it's like, well, let's look at historically. Nobody cared about, in computer vision, nobody cared about CNNs until ImageNet and Pascal, right? So I think it needs to be something that actually solves a fundamental vision tasks better than other methods, right? And I think there's plenty of opportunities, because frankly, computer vision is a little bit stuck right now. And the fact that, like, we know, for example, that you take, I think a lot of people overestimate how good computer vision is. So yes, we have 85% performance on ImageNet. But if you take that ImageNet detector and you just run it on just random, you take it, put a wearable camera and walk outside, on the street and just keep running it, performance drops to about 25%. Okay, and it's not like saying, oh, it's a different domain. That's not really true, because the whole point of training, you're training to to detect cars. You're not training to detect ImageNet cars, right? So as a part of actual, realistic scenario, this should be working. And I think getting this to work, one way of getting this to work is this kind of a continual learning paradigm where maybe you start with ImageNet, but then you just keep getting better and better so that you can actually get a reasonable performance on normal, walking around the town data. I think if we see something like that, that would definitely get vision people notice, because that is one thing that everybody is very well aware of. That like all of these methods that work great on fixed data sets, they fail miserably in the real world. And I think continual learning is one way to try to address that.
So I have one final question. So there's the final question is, what is the connection between self-supervised learning and continual learning?
I mean, for us, we are using self-supervised learning as a tool, and to get ourselves to adapt in this kind of a continual online way, because self-supervised learning can give us labels directly from the data. Now, if we had, a little oracle that would give us a true label, 24/7 for every single frame, yeah, we wouldn't need to use self-supervised learning. So self-supervised learning is basically like a little crutch, because we don't have real ground truth labels. This is like our way of going around this problem. It is basically just a tool. I suspect there could be other tools also.
All right. So thank you very much for this wonderful talk, and thank you for being with us today.
Thank you.
Really enjoyed this. So our next session, it is actually my absolute pleasure to introduce our next spotlight and the final spotlight of the day, which is titled Anatomy of Catastrophic Forgetting, Hidden Representations and Task Semantics. This paper received our Best Paper Award, so congratulations.